Before you fall asleep tonight, consider this: every light in your home, every screen you've ever stared at, every heartbeat in your chest, every memory firing inside your brain. All of it depends on something so small that it cannot be seen, photographed, or sliced into pieces. It has no known size in the way a marble has size. It has no internal structure that we can detect. It does not spin the way a tiny planet spins. And yet, without it, America's cities would go dark, chemistry would collapse, atoms would disintegrate, and matter itself would quietly unravel into nothing familiar. That something is the electron. We talk about electrons casually in classrooms from California to New York, in engineering labs in Texas, in research centers in Massachusetts. But tonight, instead of using the word and moving on, we will pause. We will slow down. We will gently ask a question that sounds simple but may be one of the deepest in all of physics: what is an electron made of? And as we let that question settle, we may discover that the smallest known building blocks of our world are not built from anything at all. If you enjoy calm, patient explorations of science like this, consider subscribing and gently tapping the like button. It helps this quiet corner of learning reach others who might need it. And before you settle in, leave a comment telling us which part of the country you're watching from. Are you listening from the Pacific Northwest, the Midwest Plains, the Deep South, New England? It's always comforting to imagine this calm space stretching across the map, connecting curious minds under the same night sky. If we begin at the surface of everyday life, electrons appear almost ordinary. They flow through copper wires in power grids stretching across the United States. They move silently through the silicon pathways of microchips. They bind atoms together into molecules that form oceans, mountains, skin, bone, breath, and blood. In high school textbooks, electrons are drawn as small dots orbiting a nucleus like planets around a star. It is a comforting image. It feels manageable. It gives the mind something to hold. But like many early scientific pictures, it is not the final story. It is a stepping stone, a soft introduction to something far stranger. To understand what an electron might be made of, we first need to understand what scientists mean when they call it elementary. In physics, an elementary particle is one that has no known internal structure. It is not composed of smaller parts. It is not built from pieces the way atoms are built from protons, neutrons, and electrons. Protons and neutrons themselves are made from smaller entities called quarks. But the electron, as far as every experiment has shown, does not contain quarks, strings, layers, or hidden compartments. When physicists collide electrons together at enormous energies in particle accelerators, energies far beyond anything found in ordinary life, the electrons do not shatter into fragments. They behave as if they are indivisible. This idea alone can feel unsettling. Nearly everything we encounter is made of smaller things. A rock can be broken into pebbles, pebbles into grains, grains into molecules, molecules into atoms, atoms into nuclei and electrons, nuclei into quarks, and then, at least for now, the trail stops. The electron stands alone without visible substructure. But what does that really mean? Does it mean the electron is truly fundamental? Or does it mean we have not yet looked deeply enough? To answer that, we must gently step into the world of quantum field theory, the most successful framework modern physics has for describing reality at the smallest scales. In this framework, particles are not tiny solid beads. They are not miniature billiard balls. Instead, they are excitations, small ripples, in underlying fields that fill all of space. Imagine the United States covered not by land, cities, or rivers, but by an invisible ocean stretching everywhere, even through empty rooms and outer space. Now imagine that what we call an electron is not an object floating in that ocean, but a vibration of the ocean itself. When the field vibrates in a specific way, with a specific energy and pattern, we observe that vibration as an electron. In this view, asking what an electron is made of may be like asking what a wave in the Atlantic Ocean is made of. A wave is not made of smaller waves inside it. It is a motion of the water. Similarly, the electron may not be made of smaller components. It may simply be a stable vibration of the electron field. This idea, though abstract, has extraordinary predictive power. Quantum electrodynamics, the theory describing how electrons interact with light and electromagnetic fields, is one of the most precisely tested theories in all of science. Its predictions match experimental measurements to more than 10 decimal places. That is like predicting the distance from Los Angeles to New York with an error smaller than the width of a human hair. Such precision gives physicists confidence that, at least down to scales of about 10 meters, far smaller than a proton. The electron shows no sign of internal structure. It behaves as if it is point-like. Not small like a grain of sand, not small like an atom, but small beyond imagination. And yet, despite being described as point-like, the electron possesses measurable properties. It has mass. Its mass is about 9·11·10 kilograms, an incredibly tiny amount but not zero. It has electric charge, a negative charge that defines much of chemistry and electricity. It has intrinsic angular momentum known as spin, although this spin does not mean it physically rotates like a spinning basketball. It has a magnetic moment, meaning it interacts with magnetic fields. These properties are not built from smaller visible parts. They are simply characteristics of the electron field itself. The idea that the electron might not be made of anything deeper challenges a common intuition that complexity always reduces to simpler building blocks. Sometimes, in physics, we reach a layer where simplicity is not about smaller pieces but about underlying principles. Still, the human mind wonders, could there be something beneath the electron? Could it be composed of even smaller entities, too tiny for our current instruments to detect? Theoretical ideas have explored such possibilities. Some speculative models imagine substructures called preons, hypothetical particles that might combine to form quarks and leptons like electrons. But so far, no experimental evidence supports their existence. Other frameworks, such as string theory, suggest that what we perceive as electrons might be tiny vibrating strings of energy, existing in more dimensions than the three of space and one of time we experience. In these models, the electron's properties emerge from the specific way the string vibrates. But again, this remains theoretical. No direct evidence has confirmed such strings. So where does that leave us? It leaves us in a position both humbling and peaceful. The electron, one of the fundamental participants in every atom in your body, may not be made of anything at all. It may simply be a basic feature of reality, a foundational ripple in the fabric of existence. If that feels abstract, consider this: every time you flip a light switch in your home, billions upon billions of electrons drift through metal wires. They do not travel at the speed of light. Their individual drift is slow. What moves quickly is the electromagnetic signal that nudges them along, like a push passed through a long line of people. Yet each electron involved is identical to every other electron in the universe. That sameness is another astonishing property. Electrons are indistinguishable. Not just similar, identical in every measurable way. The electron in a hydrogen atom in Florida is indistinguishable from one in a distant galaxy billions of light years away. They share exactly the same mass, the same charge, the same spin. This perfect uniformity suggests something profound. Electrons are not manufactured objects, assembled in cosmic factories. They are expressions of a universal field, the same everywhere. As we rest with this thought, the question subtly transforms. Instead of asking, what is the electron made of, we begin to ask, why does the electron field exist at all? Why does nature include this particular vibration with this precise mass and charge? Why not something slightly different? These are questions at the edge of modern physics. Some answers may lie in deeper symmetries of the universe. Others may remain mysteries for generations. But for tonight, in this calm exploration, it is enough to understand that the electron is not a tiny solar system object, not a solid speck with internal gears. It is a quantum excitation, a fundamental unit of charge, a stable ripple in a field that permeates the cosmos. And within that quiet realization is something beautiful. The smallest known component of chemistry, electricity, and life itself may not be built from parts. It may be one of the final notes in the symphony of matter, simple, indivisible, and essential. As Theodore, our patient researcher, might whisper into the night, sometimes the deepest mysteries are not hidden inside things, but inside the question of why there is something rather than nothing at all. And with that thought gently unfolding, we continue our slow journey inward, toward even deeper layers of understanding. If in our first chapter we allowed the image of the solid, tiny bead called the electron to gently dissolve, here in the second chapter we will take one step deeper into the quiet structure beneath that dissolution. We will move more slowly now, as if descending beneath the surface of a calm lake, watching the familiar sunlight of classical intuition fade into something more subtle and expansive. Because if the electron is not made of smaller pieces, then what truly exists in its place? What is the substance? If we can even use that word, of something that behaves like a point and yet fills textbooks with equations and laboratories with careful measurements. Modern physics offers a remarkable answer. What truly exists is not primarily particles but fields. And not fields in the casual sense of grassy plains stretching across Kansas or Nebraska, but physical quantities that exist at every point in space and time. A temperature field assigns a temperature to every location in a room. A gravitational field assigns a gravitational pull to every point in space. In this deeper description of nature, there is also an electron field, extending everywhere, through your walls, through your body, through the vacuum between galaxies. This is not poetic language. It is the formal structure of quantum field theory, the framework that underlies our most precise predictions about matter. In this view, the electron you learned about in school is not a tiny object traveling through space like a grain of dust drifting through sunlight. Instead, what we call an electron is a localized excitation, a quantized vibration, of the electron field. It is a ripple that carries energy, momentum, charge, and spin. To appreciate how radical this is, let us consider something familiar. Imagine a football stadium filled with tens of thousands of people. The crowd is calm, sitting quietly. Then, somewhere in the stands, a person stands up and raises their arms. That motion spreads. One by one, people rise and sit in sequence, creating a wave that travels around the stadium. The wave moves, but the people themselves mostly remain in their seats. The wave is not an object separate from the crowd. It is a pattern of motion within the crowd. In a similar way, the electron may not be a separate thing, traveling independently through empty space. Instead, space itself contains the electron field. When that field vibrates in a particular quantized way, we observe what we call an electron. Now, you might gently ask, what is this field made of? And here we encounter a subtle shift. In classical thinking, we imagine fields as being made of something, perhaps invisible fluid, perhaps tensioned fabric. But in quantum field theory, the field is not made of a deeper material. The field is fundamental. It is part of the basic structure of reality. There is an electron field. There is also a photon field whose excitations we observe as particles of light. There are quark fields, neutrino fields, gluon fields, and more. Together, these fields form what physicists call the standard model of particle physics, the most successful theory ever constructed to describe the microscopic world. Within this model, the electron belongs to a category known as leptons. Unlike protons and neutrons, which are composed of quarks bound together by the strong nuclear force, leptons show no sign of internal structure. High-energy experiments have probed electrons at scales down to roughly 1,000th the size of a proton, and still they appear point-like. Let us pause here and imagine what that means experimentally. At facilities such as large particle accelerators, scientists collide electrons with other particles at extremely high energies. The higher the energy, the shorter the wavelength associated with the probing particle, and therefore the finer the detail that can be resolved. It is similar to how smaller ripples in water can reveal finer features of a submerged object. Yet even at these extraordinary energies, no internal substructure has appeared. The electron behaves as though it occupies no volume in the classical sense. It does not have a measurable radius. If it does possess structure, that structure lies at scales smaller than we can currently access, smaller than about 10 meters. To put that in perspective, if an atom were expanded to the size of the continental United States, an electron's possible upper size limit would still be far smaller than a single grain of sand. And yet, paradoxically, the electron is not nothing. It has mass. It resists acceleration. It carries charge. It participates in electromagnetic interactions. It influences magnetic fields. It obeys the probabilistic laws of quantum mechanics. How can something with no known size and no internal parts have such defined properties? The answer lies in symmetry and interaction. In quantum field theory, the properties of particles arise from the mathematical symmetries of the fields themselves. The electron's electric charge is not a tiny object glued onto it. It is a manifestation of how the electron field interacts with the electromagnetic field. Charge is not an ingredient. It is a relationship. This perspective changes the question. Instead of asking what the electron is made of, we begin asking how the electron field behaves within the network of all other fields. The universe becomes less like a construction of nested objects and more like a dynamic tapestry of interacting vibrations. One of the most important interactions shaping the electron's existence involves the Higgs field. This field permeates all of space, just like the electron field. When particles move through the Higgs field, they acquire mass through their interaction with it. The electron's mass, that tiny but measurable 9.11 tos 10 of kilograms, arises because the electron field couples to the Higgs field with a specific strength. In other words, the electron is not made of mass. It gains mass by interacting with another field. Without the Higgs field, electrons would be massless, moving at the speed of light, unable to form stable atoms. Chemistry would not exist. Stars would burn differently. Life, at least as we know it, would be impossible. As we breathe slowly and let this settle, we can appreciate how delicately balanced these interactions are. The electron's mass is not arbitrary in everyday consequences. If it were significantly heavier, atoms would shrink, chemical bonds would alter, the structure of matter would shift. If it were lighter, atoms would expand, stability might weaken. The very periodic table might rearrange itself. And yet, despite this importance, we do not know why the electron's mass has the value it does. The Standard Model allows us to measure it and calculate its consequences with extraordinary precision, but it does not explain why that number is what it is. It simply accepts it as an input parameter. There is a quiet humility in that admission. Even our most advanced theories contain mysteries at their foundation. Now let us consider another property, spin. The electron has spin 1/2, expressed in quantum mechanical units. But this does not mean it is physically spinning like a top. In fact, if one tried to imagine a classical sphere spinning fast enough to account for the electron's measured magnetic moment, the surface would need to rotate faster than the speed of light, which is impossible. Instead, spin is an intrinsic quantum property. It is built into the mathematics of the electron field. It determines how electrons behave under rotations and how they obey the Pauli exclusion principle, the rule stating that no two electrons can occupy the same quantum state simultaneously. This principle is responsible for the structure of atoms, the stability of matter, and the entire architecture of chemistry. Without spin 1/2, electrons would not stack into distinct energy levels around atomic nuclei. The periodic table would dissolve into chaos. Matter might collapse into denser states. The familiar solidity of your desk, your phone, your own body, depends fundamentally on this quantum property. And yet spin is not composed of smaller spinning pieces. It is fundamental behavior emerging from the symmetry of space itself. Perhaps at this point, the question, what is an electron made of, begins to feel less like a mechanical inquiry and more like a philosophical doorway. Because if the electron is a quantized excitation of a field, and the field itself is fundamental, then the electron is not built. It simply is. But science remains cautious. History reminds us that what once appeared fundamental sometimes revealed deeper layers. Atoms were once thought indivisible. Then came electrons and nuclei. Protons seemed fundamental. Then came quarks. It is possible that future experiments may uncover substructure within electrons. New physics beyond the Standard Model may one day reveal hidden layers. Some theoretical frameworks predict that at incredibly small scales, near what is called the Planck length, around 10 Bohr meters, space-time itself may become quantized or foamy. In such regimes, our current understanding of fields may break down. The electron, as we describe it now, may emerge from even deeper principles not yet understood. For now, though, all experimental evidence tells us that the electron behaves as an elementary particle. No cracks have appeared in its apparent simplicity. And so, as Theodore might reflect in his quiet study late at night, the mystery is not merely what the electron is made of, but why nature chooses to have such a field at all. Why should reality include this precise vibration, with this precise charge and mass, capable of forming atoms and enabling consciousness to ask questions about itself? There is something profoundly moving about that. The electrons in your brain right now, shifting gently across synapses, enabling thought, are the same type of excitations that shimmered in the early universe billions of years ago. They are the same in distant galaxies whose light is only now reaching Earth. They are uniform, identical, and timeless in their properties. In the quiet hum of a refrigerator, in the glow of a bedside lamp, in the subtle electrochemical pulses of your nervous system, electrons participate continuously in the unfolding story of matter. They may not be made of smaller building blocks. They may instead be one of the deepest notes in the symphony of fields that compose reality. And as we allow that thought to rest gently and without urgency, we prepare to go further still, toward the frontiers where current theory begins to blur, where speculation meets mathematics, and where the question of fundamental structure opens into the vast unknown. What is an electron made of? We have traveled from the familiar classroom image of orbiting particles to the deeper landscape of quantum fields. We have seen how the electron shows no measurable size, no detectable internal structure, no smaller pieces hidden inside, at least not at any scale our most powerful instruments can probe. We have explored how its mass arises from interaction with the Higgs field, how its charge reflects a fundamental symmetry of electromagnetism, and how its spin shapes the architecture of atoms and the stability of matter itself. And now we arrive at a gentle but profound possibility. Perhaps the electron is not made of anything at all. In the modern understanding of physics, the electron is described as a fundamental excitation of the electron field, a stable, quantized ripple in something that fills all of space. If this description is correct, then asking what the electron is made of may be like asking what a musical note is made of. The note is not composed of smaller notes hidden inside it. It is a pattern of vibration, a structured movement, a defined resonance. The electron may be one of the simplest resonances nature allows, but science is never fully closed. The history of physics teaches humility. There was a time when atoms were believed indivisible. Later, protons were thought fundamental. Each time we believed we had reached the smallest layer, a deeper one revealed itself. So it remains possible, quietly, patiently possible, that electrons may one day reveal substructure. Perhaps future accelerators will reach energies high enough to expose hidden layers. Perhaps new mathematics will show that the electron emerges from even more primitive ingredients. Perhaps space-time itself will prove to be woven from something more basic still. Yet as of today, every experiment agrees the electron behaves as an elementary particle. It does not fracture. It does not stretch. It does not reveal edges. It responds as a point-like entity whose properties are fixed and universal. And there is something deeply elegant in that simplicity. Consider the astonishing consistency of electrons across the cosmos. The electron in your body tonight, quietly maintaining the structure of atoms in your cells, is indistinguishable from electrons billions of light years away. They share identical mass, identical charge, identical spin. They obey the same equations. They respond to the same symmetries. The laws that govern them appear uniform across space and time. In this sense, electrons are threads of continuity woven through the entire universe. They connect the birth of stars to the chemistry of oceans, the fusion in stellar cores to the electricity in city lights, the earliest moments after the Big Bang to the thoughts forming gently in your mind right now. And still, beneath that unity remains a mystery. Why does the electron field exist? Why does it have the strength of interaction it does? Why does it couple to the Higgs field in precisely the way that gives it its particular mass? The Standard Model describes these features with extraordinary precision, but it does not yet explain why they are so. Perhaps those answers lie in deeper symmetries not yet discovered. Perhaps they emerge from principles so simple that, once revealed, they will feel almost inevitable. Or perhaps reality at its foundation simply includes certain basic ingredients, fields that exist not because they are built from something else, but because they are part of the fabric of existence itself. It is humbling to recognize that our most refined understanding still rests upon foundations we cannot yet explain. And yet, there is peace in that boundary. The electron does not need to be made of smaller parts to be meaningful. Its simplicity does not diminish its significance. In fact, its apparent indivisibility may be what allows the stability and complexity of everything else. From that single type of excitation emerges the vast diversity of chemistry. From chemistry emerges biology. From biology emerges awareness. And from awareness emerges this very question. In the end, perhaps the electron is not a puzzle piece waiting to be broken apart, but a fundamental note in a cosmic harmony, a vibration that simply exists consistent and unwavering across the immensity of space and time. So tonight, as you prepare to rest, imagine the quiet presence of electrons surrounding you and within you. Not as tiny spinning beads, not as miniature planets, but as gentle ripples in fields that stretch endlessly across the universe. Ripples that have persisted for billions of years. Ripples that make matter stable, light visible, thought possible. We set out asking what the electron is made of. We arrive at a softer realization. Sometimes the smallest things are not made from anything deeper. Sometimes they are the depth. Thank you for spending this time in patient curiosity. Wherever you are across the country tonight, beneath city lights, open skies, coastal winds, or mountain air, May your questions remain gentle, your wonder steady, and your rest peaceful. And in the quiet hum of the world around you, the electrons continue their silent work, unchanged, fundamental, and beautifully simple.